The above expression for the dielectric constant of a free electron gas has a singularity at q equal to 2 kF. This singularity has very important consequences. This singularity at q equal to 2 kF has very important consequences. Let us see what it is. For example, let us look at a metal. Metal has got these ion cores which are actually vibrating. So, I have a metal, this has ion cores which are vibrating, and let us call u of r minus Rn the displacement of the ion core at Rn. So, just as we did for the energy band calculations while writing down the tight binding wave function, I can also write down a u of q which is given by, so this will be actually the normal mode vibration, and this is given by sigma over n over sum over all the lattice sides e to the I q dot Rn, so this q is a vector, times u of r minus Rn, where u of r minus Rn is the displacement at the lattice site Rn. Now, supposing I consider only one particular mode of vibration, then I have a potential that is actually causing a perturbation, and this potential is given by u of r comma t is equal to, as before, u of q e to the I q dot r e to the I omega q t times e to the alpha t, just as we had before. Now, what happens is that the dielectric constant epsilon q screens this potential. So, usually the potential between the two atoms in this particular vibrational mode is actually screened by epsilon q, or let me put epsilon q as a function of q, because that is the way we have used it before. Now, at q equal to 2 kF, there is a singularity in epsilon q. So, what this singularity does is this reduces the interaction potential for the qth normal mode, q equal to 2 kF normal mode, drastically, because epsilon q comes in the denominator and epsilon q is showing a singularity, that is, it is going towards infinity, and so this is going to be reducing the interaction potential. So, this means that the mode omega q softens, that is, the vibrational frequency corresponding to q equal to 2 kF softens. So, if this softens, then this effect is called cone anomaly, and there can be cases where this could also lead to structural change. Let us see how this happens in one dimension. So, we saw that in one dimension what happens is that the 2kF is equal to pi by 2 pi by a, no, pi by a, sorry, let me see, let me think about it. I have the energy band which is given by the following. So, I have E versus k, and this is pi by a, this is minus pi by a, and if the band is half filled, then I have all the states up to minus pi by 2a to pi by 2a are filled, and this is the Fermi level, and so I have 2kF is equal to pi by a. So, if 2kF is equal to pi by a, then what happens is this distortion, this softening of the 2kF vibrational mode leads to a dimerization of the lattice. So, what we mean by softening is actually when the frequency goes to 0, then the restoring force is almost 0. If the restoring force is 0, then when the atoms move apart, they cannot come back, and so there is a static distortion, and this is the dimerization in this case. And when this dimerization of the lattice occurs, then new gaps are opened up in K space corresponding to new Brillouin zones. So, now supposing I have a dimerization, the new Brillouin zones are now minus pi by 2a and pi by 2a, and so I will have a gap opening up here. So, because this becomes the new Brillouin zone, and I have a gap opening up here. Let me write down better. So, this is the gap that opens up, and the lower band becomes completely filled. This lower band becomes completely filled, and the system becomes an insulator. This is the Peierls instability. In one dimension it was shown that in one dimension this is unconditional, this instability is unconditional. What we mean by unconditional is that no matter how stiff the lattice is, the electronic energy gain due to dimerization is greater than the strain energy cost. So, this is something that we actually discussed when we were initially discussing the one dimensional energy bands. Now, the issue is the following: is it true even in higher dimensions. The point is, it is not necessarily true in higher dimensions. The reason is the following. In one dimension, the Fermi surface is 2 points. In our case, it was at pi by 2a and minus pi by 2a. So, these were the 2 points that were there in the one dimension. So, a distortion such as dimerization in this case leads to all the electrons at the Fermi surface getting stabilized. Which means you have maximum electronic energy gain due to distortion, maximum possible electronic energy gain due to distortion. For example, if the 1D lattice was, for example, 1D lattice was 1/3 filled, means 2 electrons for 3 orbitals, then a trimerization will occur. You can also see it in the following sense, in a molecular orbital picture. If you want to see it, what is happening is the following. See, you have 3 orbitals which are all degenerate, okay, and then you have 2 electrons. Let me put it as up and down. So, this goes to trimerization, which means that you form molecular orbitals. These molecular orbitals will be the following, that is, I have a bonding molecular orbital, a non-bonding molecular orbital, and anti-bonding molecular orbital, and now both the electrons will go in here, so that there is a complete stabilization, maximum stabilization of the system because of trimerization. Now, what happens in, say, for example, a 2-dimensional system? In the 2-dimensional system, the Fermi surface is actually like a circle. For free electron gas, the Fermi surface is a circle, and let us assume that it continues to be a circle. So, this is the Fermi surface, and now supposing, and let us assume that this has the radius of the Fermi surface k is equal to pi by 2a comma pi by, I am considering a square lattice of size a. So, the radius is going to be just pi by 2a, and now when I dimerize it, what I am going to do is introduce new Brillouin zone planes at pi by 2a and minus pi by 2a. So, initially it was actually pi by a was the radius of the Fermi surface. It was not pi by 2a, it was pi by a, okay. And now what you are doing is you are introducing, say, you are introducing planes in the Brillouin zone corresponding to pi by 2a on this side and on this side as well. So, what happens is that the states at the intersection of the new Brillouin zone planes and the Fermi surface are stabilized. Others are not affected very much because they are only very minor, probably second order perturbation corrections will be there, and since there is no degeneracy, there is no gap that is opened up in those places. So now what happens? So very few electrons are stabilized. So the electronic energy gain is not a maximum. Gained by electrons is not large or not large enough often to offset strain energy. And this can also happen in 3D. For example, in 3D, if you have a Fermi surface in 3D is a sphere, then what happens is that, I'm drawing the sphere and the circle both in the same way, so you have to be careful. So supposing I'm looking at it this way, then I have the planes opening up here, and the circle that's on these two planes. So all the states on the circumference, all the states on the circumference get stabilized. Even this is a small fraction of all the electrons on the Fermi surface, so one is not sure whether this is going to lead to Piles type of distortion. But on the other hand, supposing I have shapes of Fermi surfaces in real systems which go like this. Okay. Then what happens is, if this is 2kF, when the shape is different, 2kF is decided by 2kF is the distance in k space between points at which the tangents to the surface are parallel. So this is the 2kF. Now what you see is that all the electrons on this surface and on this surface, which is fairly large, so a large number of electrons will get stabilized. Will get stabilized due to the above 2kF distortion, and the electronic energy gain is significant. So these kinds of Fermi surfaces are called nesting Fermi surfaces. These types of Fermi surfaces are called nesting Fermi surfaces. And one of the aims of energy band theory is to look for Fermi surfaces which are nesting in order to predict whether there is going to be a distortion in the system at t equal to 0 k. So these are called nesting Fermi surfaces, and energy band theory is used to see whether a material has nesting surfaces, whether a material has nesting Fermi surfaces. Well, so when you have nesting Fermi surfaces, then you have giant cone anomaly or piles type of a distortion. This is known in quasi one dimensional and quasi two dimensional systems. For example, TT, FTC and Q is a quasi one dimensional system, has nesting Fermi surfaces, and this has piles distortion. Now what we will do is we go over to a slightly different question we will ask ourselves, and this question is important because we want to know what is the meaning of crystal momentum. So let me just say, call the topic as crystal momentum. So when you have free electrons, H naught is equal to minus h cross squared by 2m del squared, and psi k equal to e to the power I k dot r, and you see that H commutes with P, and hence e to the power I k dot r is also an eigenstate of P. The eigenstate of the operator P, and the momentum is given by the electronic state that the system is occupying. Momentum is given by H cross k. Now what happens in a periodic potential is, when we have a periodic potential, have a periodic potential, the H crystal is equal to H naught plus V of r, where V of r plus Rn is equal to V of r. Rn is a lattice translation vector, and V of r is periodic in lattice translation, with periodicity given by lattice translation vector. Now in this case, what we have is the eigenstates are given by the Bloch's theorem tells us what the eigenstates should look like, and the eigenstates are given by psi k of r is equal to e to the I k dot r u k of r, and u k of r has the periodicity of the lattice. Now the point is, does the k index in the eigenstate of H crystal give the momentum of the electron? Well, the answer is an emphatic no. Why is that? So that is because H crystal comma P is not equal to 0. That is because V of r does not commute with P. So, then in that case what is this k? Well, when we did the tight binding calculation, and initially when I gave you all the pictures of the energy bands as wave functions, as this thing overlaps of atomic orbitals, then we saw that the k in the crystal eigenstate denotes the phases with which the orbitals overlap in a band. In a band to give crystal orbital, you can say. For example, for k equal to pi by a in one dimensional lattice, you had the real part of the wave function could be written in the following way, that is the overlaps were such that the wave function was going this way, sorry. So, the real part of the wave function would go as the following. The wavelength lambda is equal to 2 pi by k equal to 2a. So, that is what we got. So, k was actually a label for the molecular orbital. K was a label for the crystal orbital and because of periodicity e to the I k dot r has the same period, sorry, it is e to the I k dot r n, because this is the phase with which the orbital at n is being modulated. So, e to the power I k dot r n is equal to e to the I k plus k m dot r n as k m dot r n is equal to 2 pi times integer. So, which meant that k was not unique, and one could add any reciprocal lattice translation vector k m to k, and the physics will not change and the orbital will remain the same. When I say orbital, I mean the crystal orbital. The crystal orbital will remain the same because all that you are going to do is the envelope function, which is actually the wave that you are writing down with k plus km, which is 1 upon 2 pi upon k plus km is the wavelength, and this new wave will have exactly pass through exactly the same points at lattice points as the old wave, which was 2 pi by k. That is 2 pi by k wave of wavelength, okay. 2 pi by k wavelength passes through same points at lattice sites as wave with wavelength two pi by k plus km. So, this is the reason why k is conserved to within a reciprocal lattice vectors. Therefore, we say K prime equal to K plus Km describes the same physics as K. What I will do is I will try to, in the next part of the lecture, what I will do is I will give you more insight into what actually this K, or the wave vector of the lattice size of the block function, actually implies in the case of a real crystal when an external field is applied, what it means, and I will discuss that in the next lecture. For now I will stop at this point. This is a convenient point to stop and start the next lecture from here on. Thank you.